All right, back at it with video problem number 4. This week's video problem, we are asked to describe or explain at least two of the following properties. So properties that I'm going to explain are going to be the first one, why the determinant is 0, if and only if A is not invertible. We are also going to talk about number 2, and we are also going to talk about number 3. So look at the first biconditional. The determinant of A is 0 if and only if A is not invertible. So let's just define some terminology. The determinant. Determinant is how the space. I use space because in R2 we're thinking area, and R3 we're thinking volume. So space will just be the overall term that we use to describe. And a determinant gives us information about how that space created by the vectors, not necessarily unit vectors, but the vectors in Rn changes after a transformation. And invertible is basically undoing a transformation. So when we say not invertible, what we are really saying is that the transformation cannot be undone. Again, thinking about matrix multiplication as a transformation. So what does it mean to be not invertible? That means we are confined to a new space that we cannot get out of. So this illustrated example shows how we go from R3 and we can transform from R3 to R2. Say we are in the volume, we are in this box, and the transformation T that we apply takes everything and compresses it into the ZX plane. So now everything in R3 originally has been compressed into the standard 2D ZX plane. So this transformation is not invertible. It cannot be undone because we are stuck in this new space. We cannot leave. We cannot simply add a y component and enter a higher dimension. After the similar thing, we think about any point in the xy plane in R2 and we transform it to a line in R1. Again, we are stuck on that line. We can no longer get anywhere in that plane. So that is, the determinant is 0. If A is not invertible, it's just kind of describing what it means to be not invertible. Second one we want to discuss is why switching rows and columns changes the parity of the determinant. And that is because it changes the orientation of vectors in relation to each other. So that's also known as inverting the space. And I hope we talk more about the actual rotation process and how this inversion takes place. Because to me, it seems like it would take place in a complex plane, but might be beyond a scope. I don't really know. But this example just illustrates, we have j hat on the right, I hat on the left, and then after a transformation, so this would have a determinant -1. And the third property we want to talk about is when we multiply a row by k, we change our determinant by a factor of k. And this can just be seen by if we have our box from the previous example and we stretch x by a factor of k, the volume of the new cube that we have has changed by a factor of k. And if we multiply, instead of just a row, if we were to multiply the entire matrix by k, the determinant in this case changes by k to the n, determinant of A, and that n is just given by what dimension we are in, so that is this n. Also easily seen by if we were to stretch every dimension of that box instead of just the x dimension, the entirety of the box would change by k to the third in this case because we are in R3. But yeah, those are